thanks a lot for having me, and sorry for joining remotely. I appreciate the effort to include me. So I'm going to present our work on literate execution. So I'm going to set the scene first by mentioning some related work that we're building on here, and then I'm going to go about the other two parts of the talk in reverse order. So I'm going to explain what we did in this paper first, and then I'm going to come back to why and what it is we're trying to do. And I think that will just segue a bit more nicely into some of the discussion, because we had some very good reviewer commentary that I wanted to discuss. So the basic idea of fluid and transparent visualizations is motivated by what you could describe as a disconnect between the world in which we do science and the world in which we communicate science. And what fluid is, the kind of angle that we're exploring with fluid, is the idea of a language that keeps track of data provenance. And fluid is a pure and Python-like instantiation of this idea. So there are some papers here on this, and you can look at those if you're interested. But I think the easiest thing to do is just to give you a couple of demos to give you the flavor. So I'm going to move to the first of my demos. If there's any problem seeing it, do let me know. Just wait for this to load. Okay, so the basic idea of a transparent visualization is that, as well as having a chart, we can access a view of the underlying data. And then I can interact with visual features in the chart to see the data that was needed for that part of the output. And I can do this the other way around. I can move my mouse around, for example, in the input, and I can see how data values in the input are being consumed by output elements. So in this case, the inputs are being highlighted in pairs, and that's because they're being consumed in pairs in order to compute the y-coordinate of these points on the right. So I'll show you the code now for this example. So we don't need to dwell on the details of this. It's fairly straightforward. The key takeaway here is that this is pure functional code. There's no mention of interactions or anything like that. They're provided in this case. So the idea then is that the programmer just has to describe how to map data to visual elements. The runtime analyzes dependencies and takes care of providing these interactions. And then the user can interact to see how demand flows backwards and how demandedness, the property of being demanded, flows forwards. So the second example is matrix convolution, and we're going to come back to this shortly. So let me show you the code first for convolution. So again, it's purely functional. The output matrix is just computed as a pure function of these two input matrices, the image and the kernel. There's no mention of interactions, but what we get is an interactive version of convolution where I'm able to open up the inputs and move around in the output to see how the inputs are being consumed by the output. And in particular, when I'm at the perimeter of the output, I can see that parts of the filter become irrelevant. And that's because the input image is behaving as though it were padded by zeros, and multiplication by zero here is just going to render some of the input elements irrelevant. And so we're kind of seeing here some of the behavior of convolution kind of surfacing through the user interface. We can do something a bit more interesting if we comment out this code and enable this code. So this is going to change the behavior of convolution. And if we reload our implementation, we'll see that we get a slightly different behavior. So if I move around in the interior of the output, I see what I had before. When I move to the perimeter now, all of the filter remains needed, and instead parts of the input image are kind of consumed differently. So the idea here is that provenance queries can reveal something of how an algorithm works. If you change the algorithm, then you get a different query behavior. So this is what we built on for this paper, and the two ideas that we've been exploring are the idea of first-class documentation that you can attach to intermediate values in a computation, and then a way of visualizing those intermediates to an end user. So again, I'm going to explain these first of all just with a demo. So let's go back to the convolution example we were just looking at. So the way convolution works is that for each element of the output, we're going to compute this intermediate matrix that has the same size as the filter. So this notation here with the slightly unusual brackets is what we call a matrix comprehension, and we use this notation to compute each of these intermediate matrices. So what we can do is uncomment this dot comment, which then attaches this piece of text to this intermediate value, and that flags it as of interest and a candidate for being visualized. So now if we reload our example, when I move around in the output, I'll see a visualization of that intermediate matrix. And finally, because this notation supports interpolation, we can mention some computed values here. And if we load those, we load that version in, then now we can, if for example we have two intermediates visible, we can tell them apart because each of them is telling us which part of the output it corresponds to. And then the last thing to mention is that with this view, I can now interact with the intermediates as well. So going left, I can see the upstream dependencies, I can see the pairwise multiplication of elements from the filter and the input image. And going to the right, I can see the downstream dependencies. So I can see that each of these intermediate values through the averaging operation contributes to the single -1 on the right. And whereas when I come to this intermediate value, I can see that each of these contributes to the single, to the one that's now being highlighted on the right. Okay, so we saw there that these dot comments tag values of interest. We have this interpolation notation for embedding content. And if you can reach an intermediate from an output selection, then we visualize it along with its dot comment. And then we also interacted with the intermediates. So the idea here is to try and nudge the implementation of convolution slightly closer to being an interactive teaching tool. So the second example I'm going to show you for this paper is going to recreate a paper from this document. So this document considered 61 climate change risks that were identified for the UK in an earlier report, and the extent to which each of those was addressed by the UK's climate change adaptation plan, which is called NAP3. So let me just show you what that looks like in our implementation. So, so what we have here is we've just focused on the data, the NAP3 actions that were assigned to a single government department called NEFRA. And then we've decomposed those by chapter from the original report, and then status, which is what the color is indicating here. And this is what's called a stacked bar chart, sorry, 100% stacked bar chart. So that means that the y-axis always, is the kind of unit value, and what we're showing is the proportion that's attributable to a particular status. So think of it as a vertical pie chart, essentially. So now, if I move around, for example, in over the actions from chapter 5 of the report, I can see their status reflected in the way that selections are induced on the input data. Okay, so that's kind of before we do anything with this dot comment infrastructure. If we now do something similar to what we did with the matrix convolution example, then we can see something a little bit more interesting. So the way we compute the height of a segment is by calculating the ratio of these two numbers and rendering it as a percentage. So what we can do is add this paragraph of expository text, which is rather than just counting the number of specific actions, it's actually going to attach the summarize the descriptors associated with each of those. And now if we load the page, then we'll have a version where if I interact with chapter 5 again, then as well as getting the data selection on the input, I can also see actually how many of those were contributing to that proportion. So here it's 7, here it's 1, and so on. And we can actually render into that paragraph, in this case, the names of the actions, or the risks rather. Okay, so that's the basic idea of what we did in the paper. So we saw here expository content that's data driven, so it's computed from the data, and the visibility of that content is determined by the way the user selects in the user interface. And there's lots of choices here about how you might go about integrating some of this documentation, and we've taken a sort of naive approach. So how does this work then? So The idea is that we build a dynamic dependence graph as the program runs, and then the information in this graph supports the interactions and the linked selections that I just showed you. So in this case, for each intermediate, we're going to have this kind of pairwise dependency on the filter in the input image, except when there are zeros. And then on this top row, we're actually going to depend on a value that we didn't see in the user interface, this additional 0 here. So this is the 0 that arises in the padding with zeros implementation. And if we kind of push this dependency graph transitively in the direction of the output, then we'll see that, as we saw, 4 in the output here depends on each of these elements that were averaged together. And the point then is that any value annotated with an app.doc that's reachable from an output selection will be shown in that intermediates pane. And you can think of this subset of the intermediates that are reachable from the output selection as another kind of selection linking, effectively. Okay, so I said I'd come back to the kind of framing and motivation at the end. So imagine we've got a computational artifact with content that we want to communicate. So this might be a data science pipeline, or it could be an algorithm or process that we want to explain. So I want to contrast two different ways that we might go about that. So the first I'm calling a depictive snapshot, and the second I'm calling a live view with progressive disclosure. So the depictive snapshot approach is the kind of conventional approach where you use text and diagrams to explain a process or make a claim. So this is kind of research papers, policy reports, news articles, and so on, but also in a sense explorable explanations, because this artifact is separate from the kind of system that it's describing. So this is the data discourse disconnect that I mentioned at the beginning. And the structure is kind of rigid and author driven. So explorables do allow, some nice flexible reader driven interactions. They can tweak parameters and see updated results. But that kind of structure is determined in advance by the author. And we can build these sorts of tools using standard infrastructure, although there are some really nice tools now for explorables that make this easier. So on the other side, the idea is slightly different. The idea is to embed or in some other way integrate expository content into the running process to try and make it more self-explanatory. So in some sense, computational notebooks are already a step towards this, but they don't really have progressive disclosure. There's a sort of linear cell structure that's established up front, and it flattens everything out into this top level structure. So we don't really have a name for the kind of the new approach we're exploring. Thinking of it as a kind of self-explanatory computation, I think it is the maybe one way of getting at the idea. But the key point is that it's a view of a real system. It's flexible and reader-driven, and it probably requires a richer kind of infrastructure that's able to leverage dependency information in order to support this kind of browsing experience. So where are we along the spectrum for this work? So we've taken some simplifying assumptions just to make a start. So there's a contrast between annotations like this that are in line or out of line in a separate document. Anchoring them to the code in this way makes it easier to keep them in sync, and the usual scoping rules of the language determine the meaning of names. But there's a big disadvantage here as well, which is that if we want to write a different exposition for a different audience, then we need a brand new copy of the code base. So that's not really kind of sustainable. However, there's some recent work suggesting LLMs can actually help with this kind of anchoring problem for out-of-line approaches. And then for the viewing of the sort of documentation, we don't really have any progressive disclosure yet. We've just got this very binary user interface. You're either looking at the intermediates or you're not. And there's a couple of technical limitations as well. There's no way to refer to the current value inside the documentation that's attached to it. So there's some redesign needed there. And the actual graph structure itself has some semantic issues, and we're going to need a more significant bit of redesign work there to address those. Okay, so really what we want to look at next is fixing some of these issues with the dependency graph, and then thinking sort of more generally about what this idea of looking at intermediates in a computation looks like. So here I've described it as a kind of notebook on demand type idea. So the idea is that the intermediates themselves are actually layered, and you can progressively drill into them and sort of reveal more of the documentation and more of the computation on an as needed basis. We're also planning a user study. So we have some people lined up to do that. It's going to be focusing on the author experience initially, and then something called intentional provenance, which is what I'm going to wrap up with. And longer term, something on change propagation, which will connect what we're doing with how people kind of usually understand explorable explanations a bit, I think. So this idea of intentional provenance is what I'm going to wrap up with. So the idea here is to take the dependency graph and enrich it with information about the operations that are actually being applied. So in this case, on the left, we might record the fact that it's a sum that was used to total these numbers and compute the height of the bar. Over here, we may record the fact that some kind of column-wise operation was being applied to compute the ratios of these points. And then I think this is another way of maybe getting a handle on what this might look like in the future. If we could expose this sort of information, we could potentially semi-automatically generate natural language descriptions of kind of what's going on. So for example, you could use an LLM to, you could use this kind of provenance information as a ground truth that you could then use an LLM to turn into natural language. So that's where I'm going to stop, and I'm really looking forward to people's thoughts.
Can you hear me?
Yeah.
Okay, cool. It's a very cool demo, but I just wonder if you have like visualizations for more complex things, like showing vectors and like more complex like matrices, and like just not just like list of numbers that are hard for people to think about in their heads.
Yeah, good question. So we have a kind of pre-built set of built-in visualizations, so kind of line charts, bar charts, and stuff like that. For matrices, we have a kind of simplistic version of matrix visualization where we assume the elements are just scalars, essentially. Whereas you can imagine, some more kind of nested structures, multi-dimensional matrices, and so on. So I think there's an orthogonal kind of piece of work in building a more sort of compositional and extensible visualization library that would, allow us to enrich the visual language. At the moment, it's just these pre-built set.
Thanks for the great talk. So once I understand what data a computation depends on, I guess my next question is going to be, how much does it depend on this data? And then I think of like, oh, I want to wiggle this thing a little bit, or and it makes me think of like automatic differentiation or computation. Do you have any thoughts about that?
Yeah, so I think you're right that there's a kind of natural quantitative generalization of this. It's not something I've looked at, but one of my collaborators is particularly interested in this space, Bob Atke, who some of you may know. So Bob's interested in the kind of connection between the dependency analysis that we do here and automatic differentiation. And I think in the kind of framework, in the setup that we're looking at there, you have a kind of parameterized analysis where you could plug in something quantitative as long as it had the appropriate algebraic structure. So you could do things like computing the extent to which you need some input, for example. So yes, good point.
So this is more like a common. There's a professor at CU Boulder. His name is Tom Ye. So he's running this online platform called AI by Hand. Can you hear me okay?
Sorry, I'm struggling to hear you a little bit. Would you mind speaking up slightly?
The professor at CU Boulder, maybe easier, just come up closer.
Yeah.
I don't know.
Testing. Can you hear me?
Yeah, I can now,
okay.
Thanks.
Yeah, so I was saying that there's a professor at CU Boulder. His name is Tom Ye, Y-E-H, okay. And he's running this online platform called AI by Hand. And essentially, it's a visualization tool, but on the spreadsheet, right? You can sort of plug in the input and output matrices on this spreadsheet, and then you can have the running math equations plug into each cell, and then you can like tweak all the input output all the input values and then sort of lay out them in a way so that students can understand like how does the multiplication happening, and then what happens when you change this and that. and it's all like just on Microsoft spreadsheet. Very intuitive.
Wow. Okay. That's
yeah.
super cool. Yeah. Tom, yeah, is that the name?
Yeah. So.
Okay, great.
See you both.
Yeah, I'll certainly check that out. Thanks a lot for that.
YEH.
Okay, we have time for one more question.
Hey, great talk. So I think a question that quite a bit of us had was, so it seems like for the sake of the explanations, it's pretty dependent on having some sort of good domain-specific graphic that corresponds to the thing that you're trying to the computation you're trying to show. And so you showed for a couple of examples. Do you have any thoughts on like the really long tail of like all these different situations that can end up, all these different concepts of how computation occurs, and like how I would visualize them?
So the interface that I've shown you is very oriented around the kind of values rather than the kind of computational content. So are you asking about richer notions of value than the ones?
Also, okay, like I have 2D matrix. Do I have another one for like 3D matrices? Do I have one for certain types of nested objects? You know? Yeah,
I think this is. I think it's related in a way to the first question. I think we do have some more general things than I've shown you, but it's kind of early days for that. I think the direction we want to go in is a compositional UI for visualization where the provenance visualization is kind of baked in. So you have this idea of selection. That's the primary kind of visual notion that you're enriching these visualizations with, is the ability to highlight areas of interest. But we want to be able to build, arbitrarily complex visualizations out of raw ingredients that kind of support that. And we don't really have this particularly compositional implementation at the moment, but we're gradually edging towards one.
All right, let's thank our speaker one more time.
Is there a good place for them to reach you if they have follow-up questions?
Yes, I'll ping some details into the Slack if everyone's on into the
Thank you. Okay.
Thank you.
We have